Now that we've finished working with supply and demand, we're going to move into the next segment of this course. This chapter will be looking at demand estimation and forecasting, in other words, regression analysis. From here on out, the course is going to have considerably more math than we've dealt with so far. But still, this is an online course. I'll try to keep it reasonable. Now in this chapter, we're going to cover roughly 5 sections. The first is going to be the basics of regression analysis, what it is and how to use it. Then we'll move on to the limitations of regression analysis, because it is important to note that while this is a great tool that we can use, it isn't perfect and there's times when we don't have the data or something else is going on that we should not be able to use it, or it's not accurate enough for us to be able to use. The next is the importance of business forecasting. So a little bit more practical. Why do we care about this? When should we use it? Then we'll look at the prerequisites of a good forecast. What do you need to be able to be confident in what you're estimating? And finally, we'll end with looking at a few forecasting techniques. Now, this chapter will definitely take some reading on your own through the textbook, but by the end of it, we should be able to understand the importance of forecasting for businesses and making decisions in businesses. We should know how to specify and interpret a regression model, so you choose what should be in there, and then what do the results actually tell you. We should describe the major forecasting techniques, so know what they are, and what their limitations are, so we know when to use them. And finally, we should be able to explain basic smoothing methods of forecasting, like moving average and exponential smoothing. In the previous chapter, when we were going through examples working with supply and demand, we used made-up numbers, made-up demand schedule, made-up supply curves, made-up elasticities of demand. Now, in real life, in business, we want to be able to estimate the real numbers. So we're going to need actual data points. We can't just rely on numbers we make up. Sure, that can help tell us, if what direction price and quantity demanded will move in equilibrium. But if you're running a business, you don't want to just know the direction. You want to know the magnitude or estimate the magnitude. So that's why we're getting to this, demand estimation and types of forecasting. And for managers, it's vital for them to use whatever tools and data are available. You may have really detailed data, or you may have, not much data for your industry. But you have to use whatever you have available to try to make these decisions. And it's important to estimate market trends, consumer demand, prices of inputs, things like that. And by having these estimates of what's going to happen, or what you anticipate will happen, you can have a leg up on your competition, especially if they don't do that sort of forecasting. So what we're going to do in this chapter is basically give you an overview of the techniques of analysis that are used in various types of studies and for different types of businesses. Now to start out, we'll begin by looking at the data. When a common term we use for working with data is the acronym GIGO. It's garbage in, garbage out. If you have bad data and you feed that into the model, no matter how good the model is, you're going to end up with garbage anyway. It's not going to be an accurate model. So statistical analyses are only as good as the accuracy of the data and the appropriateness of the model itself and the variables that you're choosing for that. So for economic studies, so the type of studies I do, I can get data that's primarily gathered by the government or by healthcare organizations. These are things that are publicly available and they're easy to work with. But this isn't done for the business, so you can't rely on governments to gather and freely disseminate detailed variables for specific businesses or industries. So you have to turn to other methods. One of those is buying data from data companies. So 2 examples they give in your textbooks are AC Nielsen and the Information Resources Incorporated, IRI. If you go to their websites, you can play around and see what kind of data they have available, what kind of offerings they have. But there are other ways that you can gather your own data. So one of those ways is a customer survey. So you can do that to all the customers that are purchasing from you. Think of when you go and you buy something and they circle something on the receipt, hey, please fill out this customer survey. Another way is, just calling a random sample of individuals, those spam calls you tend to ignore. Not the ones for the car warranty being expired, but often we'll get them. I get them periodically asking me about a product I bought or might have purchased. Another thing you can do is focus groups. Sometimes big companies will do these, or like the data companies like AC Nielsen or IRI will bring in small group of people, show them like a potential new product um, or a product that already exists, and get their feedback. What do they like about it? What don't they like about it? That doesn't give you a lot of data points that you can use for reliable estimations, but it gives you very in-depth and detailed information. So you have to there's a trade-off there, and you need to think what data is more appropriate for the question you're trying to answer. Now, the growth of technology allows stores to get data as it's coming in, so at the point of sale, and you can track their inventory and sales in real time, which is really useful, especially for being able to see trends as they're happening, see changes as they're occurring, and so they can obviously purchase more from suppliers so you can keep the shelves full. And the last point I want to talk about before we move on is big data. That's become a buzzword recently. And it's sort of a nebulous term. There's a lot of different ways people define it. Some say it's too big to be handled by Excel, which is only partially a joke. Once you get a certain number of data points in Excel, it crashes or you just can't use it. The best definition is that there's a massive amount of data that's being generated. It's being generated quickly, and there's a variety of data. So it's from text, audio, video, websites, blogs, whatever. So let's see here. Network World calls it the 3 V's. So volume, velocity, and variety. So when you analyze data, you can use simple descriptive statistics. So like mean, median, mode, range, things like that, that are simple estimations that you can do in Excel, to more difficult things like regression analysis. So we'll cover some introductory work with regression analyses in this chapter. So regression analysis is a technique that's commonly used by economists to estimate consumer demand with available data. And we also use it in a lot of other applications than just consumer demand. Pretty much any paper that I write that's being published in a journal, I'm using regression analysis for. Your textbook calls regression analysis a sophisticated inferential multivariate analysis. May sound like a mouthful, but we can break down a couple of these words. Inferential, you're trying to make an inference or an estimation of what's going to happen. Multivariate means there's going to be multiple variables. We're not just looking at one variable, the effect of one variable on another. We're going to be including other variables as well. And we'll talk about why we want to include those later. Now there's 2 types of regressions. There's the third that I included only because I'm probably going to mention it in this chapter as an example, but that's not going to be something we're working with. So the 2 main types that are in this chapter and you'll be tested on are cross-sectional analyses and time series. So cross-sectional analysis is you're looking at several different variables over one single period of time. In time series, on the other hand, you're analyzing a single variable over multiple periods of time. So how does one thing change over time versus the relationship of several things in one period of time? Now, panel data is just a combination of that, so you have a bunch of cross-sections over time. All right, so let's make this a little bit more clear with an example. So let's try to estimate the demand for pizza in college towns. So ideally, when we're trying to run a regression and do this analysis, every single variable that we think is going to have an impact on demand should be included in the regression. Unfortunately, this can't happen in reality. Often variables we need to include in a regression, we don't have the data for, or it's too expensive to gather or create the data. Sometimes what we can do is have what we call proxy variables, or variables that approximate the thing that we're trying to actually measure, that it's similar enough or somehow related to it that we can use that instead. Other times we're forced to just exclude these from our regression entirely. So let's say that we've gathered the following data through a survey that we send out in, let's say, in November 2020. Because this was done in November 2020, there is just one period of time, so this will be a cross-section analysis. So let's say we have the average number of slices consumed per month by students, the average price of a slice of pizza in places that sell pizza around campus, the annual tuition cost at that school, the average price of a soft drink sold in those places that sell pizza near campus, the location of the campus, so we'll have what's called a dummy variable, so suburban or rural, and the type of college. So is it a residential college where students, most of them live on campus, or is it a non-residential, commuter school? Now, data for this question can be found in table 5.3 in your textbook. It's a little too much to put, on a PowerPoint slide. So let's think through, why did we select these variables? All these variables are due to the economic theory of demand. That's where it came from, that we're trying to capture through this. So obviously we're curious about the quantity of pizzas being sold. We need to know the price of those pizzas. The tuition cost, or the price of tuition, we're including that to try to understand or try to get at the income of the students, how much money they have to spend. Obviously that's not perfect. It'd be much easier to just ask them, how much money do you have and how much money does your family have? But in a lot of cases it isn't practical, or maybe we think that students won't answer it accurately. So we try to use tuition, again, as a proxy variable. Now the price of soft drinks, why do we include this? Soft drinks are a complementary good, so we tend to buy, pizza and soda together. So the price of soda is going to influence the quantity demanded of pizza. And then we include the dummy variable for urban versus suburban. And we do that because, the location of the campus might determine what or how high demand is for pizza. You can imagine if you have a school in an urban environment, there's a lot of other restaurants around. Students have a lot more options. So you expect them to have relatively lower demand than if you were in a place like Loretto, where pizza is pretty much your only option in town. And finally, the residential versus a more commuter-based school. You would expect that, at a school where more students live on campus, that you're going to have them staying around more and ordering pizza from local restaurants versus, driving home 20, 30 minutes, going somewhere else, or eating with their parents, or eating with, their wife and kids, something like that. Now again, these aren't the only things that are going to influence the quantity of pizza that students in a college town, how much they're willing and able to purchase. But for some of these other things, we may not be able to gather the data for it, or it may be too costly. And like I said, we may not trust people in a survey to actually answer. Here's an example of a simple multivariate regression. So we have the equation here, y equals a plus b1 times x1 plus b2 times x2 plus b3 times x3 plus b4 times x4. So y is going to be your dependent variable. So in this example, looking at pizza, it's going to be the quantity demanded of pizza. Now a is your constant, or your y-intercept. Basically, if every other variable equals 0, then that's going to be what's demanded. So basically, you can think of it as the baseline demand. Now the x's here, so x1, x2, x3, x4, these are independent variables. These are what we're using to explain y. In our pizza example, we're going to have 5 independent variables, or 5 different x's. Maybe the price of a slice of pizza, the tuition, the price of the soft drink, the urban and the residential variables. Now the b's in this, so b1 through b4, are going to be our regression coefficients. So this is a number that's actually going to measure the impact of the independent variables. So if our main question is, what is the effect of the price of a slice of pizza on the quantity of the slices of pizza that are demanded by college students, we're going to say that the price of a slice of pizza is our variable of interest. The other variables, we're going to call them control variables. We're not interested in them, but we need them included in the regression to take account for these other things that are going on. Because we could expect, if we're looking in this example at 30 different colleges, there's going to be some differences between those colleges. There's going to be different cost of tuition, again, getting at that average income of the students and their parents. How much spending power they have is going to vary between school. The price of soft drink, odds are that's going to vary at least somewhat between the different restaurants around there and between schools. And the environment they're in and what kind of students they attract, these are also going to be varying between schools. So we need to include these to account for those differences. But when we do that, if we're trying to estimate, again, the effect of price on the quantity demanded, then what we're going to look at is the coefficient for price. What is the value of the coefficient? Is it positive or negative? So if it's positive, the price increases, the quantity demanded is going to increase. If it's negative, if the price decreases, the quantity demanded decreases. And the magnitude of that coefficient is going to tell us how strong of an effect the price has on the quantity demanded. So when we interpret the regression results, we'll look at the values of the coefficients. So if we have a negative coefficient, that shows that the independent variable, when that changes, the dependent variable, y, is going to change in the opposite direction. So again, in our previous example where we had the quantity of slices is our y variable, and the price of slices is our independent variable that we're interested in. If it's negative, we're going to see those change in the opposite direction. So as price falls, the quantity demanded increases, and as the price increases, the quantity demanded falls. Which, remembering the law of demand, this is what we would expect. We expect the negative relationship. On the other hand, if we have a positive coefficient, then that means when the independent variable changes, the dependent variable y changes in the same direction. So that would be if the price increased, the quantity demanded would increase, or if the price decreased, the quantity demanded would decrease. So in this case, this is showing the reaction in the quantity demanded, the responsiveness in the quantity demanded to a change in price. So the regression coefficient here for the price of a slice of pizza is going to be, we'll use that to compute the elasticity for a price elasticity of demand. Now the next video is going to be me walking you through how to run a regression and then do the analysis and interpret the results in Excel. Excel doesn't give us a good opportunity. It's not well set out to walk through going and calculating the price elasticity of demand. And that's one of the steps you're going to need to do for your problem set. So I'll walk that through you here quickly. So now we have an equation that we estimate. We estimated the coefficients. And then let's say that we want to estimate the price elasticity of demand at a non-residential college in an urban setting with a tuition of $14,000. The average cost of a pizza slice equals $1, and the average cost of a soda equals $1.10. Well, what we can do is plug each of these into the variable. So the $14,000 tuition, the average pizza slice of $1, all those things. Put them into the equation, and then we just, we do the math. So we estimate that for when, all those variables are at the level, I just said, the quantity demanded of pizza slice is going to be $10.99. When we get that answer, we can do the point elasticity demand. We can calculate that at that given point. Remember, the price elasticity of demand using the point equation is sigma x equals the derivative of q with respect to the derivative of x times x divided by q. Now, you don't have to do any calculus for this. The derivative of q with respect to the derivative of x, the dq dx thing, that is just going to be the coefficient for the variable of interest here. So right now we're doing price elasticity of demand. So that's going to be the coefficient for the price variable. So the coefficient for the price of a slice of pizza, that variable was negative 0.093. So we do that times x divided by q. The x is going to be the actual price we're worried about. So in this case, it's 100 cents or $1. And then divided by q. The q we just estimated at this point to be $10.99. So we have negative 0.093 times 100 divided by 10.99. When we do the math, that's going to equal negative 8.42. Then all we have to do once we get this is negative 0.842 greater, is the absolute value of that greater than or equal to 1? It's less than 1. So it's going to be relatively inelastic. We can say the price elasticity of demand for the slice of pizza for a non-residential college in an urban setting with $14,000 tuition with the average pizza slice of $1 and average soda price of $1.10, it's relatively inelastic at this point. So you may think your model is great. You get these results, and it turns out you thought through all the potential variables. And not only have you considered all of them, but you've gathered data for each of them, so you're able to include everything that you think you could possibly need in your model. After you run it, you have a high R squared, you have a large sample size. You think this is great, this is perfect, but there's still potential pitfalls that we need to talk about. The three main challenges that we're going to discuss in this chapter are the challenges of identification, multicollinearity, and autocorrelation. The first challenge we face, and probably the most difficult for trying to estimate demand, or to analyze demand for a particular good or service, is the identification problem. So when we're trying to estimate demand, we could produce biased results if there's simultaneous shifting of supply and demand curves. So for an extreme example, if we imagine we have a scatter plot showing the relationship between the price and the quantity demanded of pizza over a period of like 20 years, and we see the data sloping upwards. Now this would, in our mind, violate the first law of demand. So we'll think, what's going on here? Why are our results backwards from what we would expect? Well, it could be that over time we have the demand curve shifting outwards. So maybe we have things like taste and preferences changing, so people want pizza more, their incomes are increasing, they can afford more pizza, there's more buyers, things like that. We're capturing all of that, and basically what you're seeing is the shape of the supply curve because we have demand steadily moving out. So to account for that, we need more advanced or more rigorous techniques, things like two-stage least squares and indirect least squares. These are concepts that we'll get into and that you don't need to know for this chapter, but it's important to know that this is a problem that exists and we do have solutions for it, should that problem arise. The next problem is what's called multicollinearity. So one of the key assumptions that we made in our multiple regression equation, where we have a bunch of different variables on the right-hand side, is that those variables are not related to each other in any systematic way or any consistent way. But if this assumption is incorrect, then we may have a problem, and it may distort the impact that we see. So let's look at an example. So suppose there's a regression model that looks at the demand for foreign luxury-made automobiles, and we want to control for price, income, and education. Think of income as a measure of, meaning consumers' income, their ability to afford these vehicles, and education as a means of taste. So more highly educated people, we assume, would be more likely to want to purchase a foreign luxury-made car. Now these may be capturing two different things, but unfortunately for our researcher here, income and education are related to each other. So as someone moves up through the levels of education, they tend to make more money. So if their values of variables tend to move up and down together, the least squares method might assign an arbitrarily high value to one and low value to the other, or vice versa. So you don't get an accurate measure of which one, or what the effect is for each one. So if two variables are closely associated with each other, it becomes difficult to separate the effect that each one has on the dependent variable. And this is what we mean by multicollinearity. There's two fairly simple ways to figure out if you have multicollinearity in your model. The first is if the regression passes the f-test, so the overall significance of the entire equation. If that passes, but we see that several of the variables aren't statistically significant, it doesn't pass the t-test, then those variables are highly likely to suffer from multicollinearity. Now the other way is to just look at the correlation coefficient between two variables. So if they're highly correlated with each other, then again your model's suffering from multicollinearity. However, it's not that big of a deal if the researcher isn't interested in the effect of those variables specifically. So in our model, or the simple model where we have the quantity demanded for foreign luxury cars based on price, income, and education, if what the model was interested in was the effect of price on the quantity demanded, and the income and education were just control variables, then it wouldn't be a big deal if we have multicollinearity there. The reason being that we really don't care what income and education, what their effect is specifically, just something that we need to control, something we need to account for in the variable so we can get a more accurate measure on the effect of price on the quantity demanded. The final challenge we'll cover is the autocorrelation problem. Autocorrelation is typically found in time series data, so it's also called serial correlation. And when a model suffers from autocorrelation, this is typically when the dependent variable relates to the y variable in a certain pattern that repeats itself. So, for instance, if we're looking at output over time, if there's a seasonal component to demand or to the production, then we'll see some form of autocorrelation. So we think of like demand for ice cream. Odds are that's going to be seasonal. People are going to want to eat more ice cream in the summer than when it's hot outside than when it's cold in the winter. So we'll end up with demand increasing in the summer, decreasing every winter, going up and down like that in a regular pattern. Autocorrelation will bias your standard errors, and you will end up believing that a variable doesn't have statistical significance when in fact it may because of the autocorrelation. One of the easiest solutions is to include omitted variables. So if you're looking at the demand for ice cream, include a dummy variable for the summertime or include a variable for the temperature, and that can reduce and get rid of the autocorrelation. One possible way to test to see if you have autocorrelation in your model is the Durbin-Watson statistic, and often this is automatically produced by the software you're working with. An additional solution is to transform the data into a different order of magnitude. Sometimes you can do data transformations like take the logarithm or natural logarithm of data of one specific variable. You could have leading or lagging indicators.